So hi everyone. I guess we'll just start now because it's 6:30, and I presume that there will be people watching the recording and everything. So we'll just start. So welcome to the third iteration of our Building Data Platforms lectures. This week's lecture is on machine learning operations, or MLOps, and let's do a quick recap of what we covered previously. So previously, last week, we covered the basics of data processing, especially in big data systems. We talked about Spark, which is a big data processing engine. We also ran through how to create ETL pipelines using services like AWS Glue and S3. And we also went through the creation of a serverless data pipeline with CDK and AWS. The services that we introduced last week include S3, Glue, Redshift, which is a data warehouse, as well as several event orchestration tools like EventBridge, as well as SQS or Simple Queue Service. So welcome. I was just going through what we covered last week, which is essentially building ETL pipelines using AWS, and as well as the services that we went through. So going back to the big picture of the data architecture within an organization, last week we ran through the services needed to kind of create a data processing workflow in AWS. This week, we're really focusing on the value layer, and in particular, creating machine learning platforms using tools like AWS SageMaker, as well as other open source tools like MLflow. So that's what we're going to go through today. So MLOps, which is the title of today's lecture, is essentially bringing DevOps practices to machine learning. So DevOps is basically a bunch of practices that help to make software delivery better, and it includes a bunch of different concepts. So let's just do a quick speed run of the different concepts that a typical DevOps engineer would need to have a mastery of. The first is understanding, what is an API. API stands for Application Programming Interfaces, and basically you can think of it as a reception point at which you can send requests. And when you send a request to the API, it then creates a workflow in the background for a server to carry out, and it returns a response that you can then use to process. So you can think of it this way. If I have a machine learning workflow, in this case, inference, for example, if I want to run inference on my model, I can send a request to an API. The API then calls inference, it returns the result, and it sends it back as a response to my client. The second concept to understand is what a container is. So a container is an abstraction of a system's OS. So you can think of it this way. So I'm sure most of you will probably be familiar with what a virtual machine is. So a virtual machine is kind of like an OS, a guest OS that is managed by hypervisor on your system OS. So containers are an abstraction beyond that. So each container basically only contains the software it needs, and you can specify this in something like a Docker file. So containers are very useful because they allow us to easily scale applications, and they're also quite useful for machine learning, as we'll see soon. So typically for containers, what you would do is you would kind of create an image. So an image contains all the software that's required for your application to run. And then from there, you would upload this image to something like a container registry. And then you can then have others in your team pull the image and then afterwards build and run the image, then serving it as a container for different services to run. Kubernetes is an abstraction even beyond containers. So it allows you to perform large-scale management of containers. And it won't really be the focus of today's lecture, but if you're in an enterprise setup, most of the machine learning workflows in terms of training as well as deployment will run on Kubernetes. So that's just something to keep in mind. CI/CD stands for continuous integration and continuous delivery, and it's essentially a lifecycle for our software in terms of the fact that we have to push our software to somewhere. So we push it to Git, for example, and then from there, Git will perform different workflows, like for example, testing, as well as building, and then deployment. And then we can codify all of this in something like a YAML file, which will then allow us to use software like GitHub Actions to kind of like run all these stages. So that's CI/CD. The last thing to really understand is the concept of observability, which is basically pooling metrics from our deployments so that we have a better understanding of how our system is doing. And yeah, so all of these concepts, CI/CD, containers, observability, having a software development lifecycle, we try to bring them to machine learning in order to make machine learning workflows better and more sustainable in the long run. So before any project, we need to first understand, why machine learning, because machine learning is kind of complicated. It requires steps such as ingesting data, performing training, and then managing deployment pipelines, as well as monitoring. Not all problems need machine learning to be solved. Some problems can just use simple heuristics or rules. But there are classes of problems that might require machine learning, and you can think of it as your typical recommendation system. Your in social media platforms, you need something to a system to recommend you new information to see on your feed, or for example, in I think social media is the best example for this. So the first concept to really understand is why do we want to use machine learning for our project? So essentially, if we identify that we want to use machine learning, there are some things that we need to understand, which is first, what do we want to predict? Do we want to predict prices? Do you want to recommend stuff to users? Second is also understanding the business value of your machine learning workflow. So for example, Google deploys fraud detection in their email systems. So our value there really is enabling our users to avoid fraud through an inbuilt machine learning system. And also, what kind of data is needed for this system to run. So for example, in the fraud detection system, you will need to take in past data, which you can then use to kind of train your model to predict whether an incoming email is fraud or not. So that's past data. We also want to know how can we incorporate new data in order to automate the process of improving our model in order to prevent it from being stale. So it's important to have kind of like a pipeline in place to automate the process of training our new models and keeping it up to date. And lastly, verifying that our model is able to be synchronized to the ground truth. So when we test our model out of sample, which means that we deploy it in the wild, we want to make sure that our model is basically predicting as intended. So these are all kind of like things to think about before engaging machine learning. And if all of these questions are answered, then we can proceed to use machine learning for our project. So the key thing that MLOps really deals with is setting up a lifecycle, and not just setting up a lifecycle, but also providing the software needed for this lifecycle to run automatically in an organization. And of course, ML is not ML without data. So the first thing to think about really is planning out access to your data. So where your data are stored, where your data is ingested from. So all of these concepts we covered previously last week when we talked about stuff like data lakes, data warehouses, as well as relational databases in week 1. So once we understand where our data is stored, for example, if we are providing a system that is trained on images, we will want to store all these images in something like an S3 bucket, which is like an object store. So then you will retrieve the images from there. And subsequently, you will need to think about how this images or this data can be processed to basically improve the quality, because raw data is usually not something that can be used. So there needs to be kind of like a pipeline for this data to be cleaned, be processed, and subsequently to be used for our machine learning model to be trained. So last week we went through the concept of setting up an ETL pipeline. So an ETL pipeline basically takes care of processing the data, taking care of stuff like removing empty data, and also like changing the columns and rows and so on to make your data more usable. So once we've done that, we kind of start like this data pre-processing stage, So this is where we kind of like prepare our data to be able to be used for machine learning. So in this preparatory stage, what you would do is if you went for the lecture on Monday, where we basically went through the process of conducting exploratory data analysis as well as feature engineering, we basically need to first do stuff like remove anomalies, remove missing data, as well as to implement like categories, for example. So implement stuff like one-hot encoding to basically, if you have a classification workflow, you need to change your data such that it can be encoded and subsequently to be used for classification. So all of this is kind of taken care in this pre-processing stage, and you could automate some of that as part of your ETL pipeline. So subsequently, after the data is cleaned and prepared, then you would also be able to basically do something very important, which is basically versioning. So one key thing to that ML practitioners kind of like do well is they are able to have clear versioning of their data because data changes over time. So we need to have some form of system in which we're able to track how our data is, when our data is from, and as well as like tie the data that we've used to train our model to some sort of like tracking system. So that's kind of important to take note. So tools that are available online for experiment tracking, like MLflow, allow us to basically do that. Something very cool that is not really well known is the concept of a feature store. So a feature store is basically to overcome certain problems that we've like observed in the early stages of MLOps, which is that teams kind of like repeat their data engineering and like feature engineering steps. So essentially to overcome this, what we do is that we have a centralized feature store for the organization, and teams can basically upload data to that feature store, and then subsequently other teams can just retrieve the features from the store and then use it to train other models. So having a feature store basically helps us to kind of have a single pane of glass for all the features that we might need to use for our ML models. So yeah, that's basically what a feature store is. Then afterwards, after we have prepared our data, we can start talking about training our data. So we can basically kind of set up something like a training pipeline. So you would typically learn in like any introductory ML course that your model is being trained using like a notebook, Colab or Jupyter Notebook. But this process isn't very scalable. It isn't very reproducible. So we need some sort of pipeline that helps us to automate the process of training our model. So that's something that tools on the cloud can help us to do, which is basically to set up pipelines that automate the process of training our model with new data. So beyond just training our model, there's also a very important step of evaluation. So when I talk about evaluation, what I really mean is when we have our data coming in and we train our model, we kind of need benchmarks to test whether our model is working. So as part of the pipeline, you need to have different tests to basically check if your model is working as intended before it gets deployed into the wild. So that is basically what a training pipeline is. And this kind of relates to the concept of CI/CD that I've mentioned earlier. So for DevOps engineers, typically we take care of a team's CI/CD pipeline. Likewise, for ML engineering, there is also the concept of applying this CI/CD pipeline. And in this case, it would have to be your training pipeline. So the next thing is when you train your model, there is a very important step, which is a step of hyperparameter optimization. And typically in any ML experiment tracking tool, you would have basically tracking for your hyperparameter optimization step. So basically, as part of this, you would, if you worked in machine learning before, you would know that when you train a model, there are certain hyperparameters that you can adjust. For example, in linear regression, you can basically change the learning rate, and from there you kind of get different results from your model training. And there needs to be some form of like tracking for that. So basically, you have experiment trackers that allow you to basically lock down each run of training, and then also lock down like what happened during the hyperparameter optimization step in each training run. So later on, we'll see how this happens with MLflow, which should be quite interesting because you'll see it being done live. So the next step of an ML lifecycle is model deployment. So you would have some form of like deployment operation. So at the start of the lecture, I mentioned that you could deploy it as easily as having an API, and from there, the API kind of acts as a service that other services can use to perform inference and then basically obtain the results that it wants. So this is basically what the deployment kind of looks like. So some things to take note is how you want your deployment to be done. So there are different approaches. One approach is to use serverless. And for serverless, what it means is that when you deploy your pipeline as an API, it basically doesn't have any compute that's running in the long run. It only starts compute when there is demand. So that's kind of the concept of serverless that I've mentioned quite a lot in the first lecture. So there is also other kinds. So that's serverless is kind of like more like real time. There's also like asynchronous and batch kind of inference. So in that case, you would basically run inference in a non-real time kind of setting. So for like latency sensitive machine learning workflows, you would typically want to deploy something like a serverless inference of kind of endpoint. Whereas for other workflows that might not require real time, you want to deploy like something like batch processing. So that's the concept of deployment. The next is monitoring. So monitoring is kind of related to the observability concept that I've mentioned earlier for DevOps. So in machine learning, what you want to monitor is basically how our system is performing as compared to the ground truth. So for example, did we overfit? Was there like kind of too much bias in the model that we've trained? We can observe that because when we test our model in the wild, we're able to see how it performs as compared to our benchmarks. So from there, we will know whether our model is overly biased. Another thing to take note is the concept of drift. So drift is where due to changes in the wild, this can be due to a lot of different things. It can be due to, for example, events that we might not have expected. So for example, COVID-19 massively changed how different actors act in the wild. There creates some form of drift that prevents our model from being accurate. And therefore, this kind of requires us to take in new data after observing and catching the drift, and then retraining and redeploying our model so that it can overcome any drift that it observes in the wild. So that's the concept of monitoring. There's also other things to take note, which is basically we can also have like alerts. So we can have some form of like alerting system where we're able to track if our model is not meeting certain benchmarks. We kind of create alerts in Slack, in email, or automatically trigger a rerun of our pipeline using EventBridge. So this creates some form of event orchestration there. Yeah, so that's kind of important, and it all ties into basically DevOps concepts. So if you look at all of this, it essentially is kind of applying DevOps to machine learning, therefore making ML much more sustainable and scalable to the wider organization. So different organizations have different requirements. Some organizations have streaming. Some organizations have batch requirements. So streaming is more for like real-time inference, where we need stuff with lower latency. Whereas batch is processing that can be taken like asynchronously. So it can happen basically whenever, and there's no like strict time requirement. So having this requirement identified kind of changes our architecture a lot, because if you were to have a streaming like architecture, you kind of need to adjust everything so that the pipelines can continually rerun and like serve inference very quickly. So one example of this is that when you deploy your application, you deploy your machine learning model, you would basically want to pay attention to stuff like memory, because if you have like in-memory databases, you would basically be able to massively speed up the deployment of your inference. So whereas for batch, you basically wouldn't have to do that because there's no strict real-time demand. So that's kind of important. and it's something to take note of before, like, planning out your platform's structure. So there are different ways to kind of like do all of this. So AWS provides this service called SageMaker, and SageMaker is kind of like the integrated ML platform that's provided by AWS for deployments. As you can see, it kind of doesn't mean like I need to use AWS for this. You can use like any cloud, and there are also like open source like implementations of these different ML lifecycle components. But in this case, we'll be focusing on AWS. So for example, SageMaker provides a lot of different tools that can be used. For example, we can leverage feature store. So we can have all our ML engineers and data scientists onboarded onto AWS, and then they can like basically centralize all their features onto SageMaker feature store, which then can be used by different teams for different purposes. SageMaker also provides endpoints, which is basically a very easy way to set up a REST API for us to run our inference for different purposes. SageMaker also has an integrated monitoring system, so we can basically monitor how our model is doing, and from there we can basically like trigger different services to run, like pipelines to basically rerun the whole training pipeline. Yes, as I said, you don't really need to use SageMaker. There are different open source implementations for everything. You could use Prometheus, for example, which is an open source monitoring tool, to basically perform like model monitoring. But at the end of the day, you kind of need to deploy everything somewhere, and you kind of need a compute to run it. So having the cloud provide this platform kind of eases everything up because you don't need to worry about infrastructure. So previously I mentioned about experiment tracking, and there are several tools. In fact, there are a lot of tools that are out there that kind of assist in the process of experiment tracking. SageMaker also has one, which is basically SageMaker experiments. But people kind of tend to swing between like weights and biases, or like MLflow. So both are really good. The key difference is one is closed source, so weights and biases is closed source, and MLflow is kind of like open source. So basically, what that means is for MLflow, you can basically take it in, and then you can deploy it on the infrastructure of your choice. You can deploy it on the cloud. You can also deploy it on your own bare metal infrastructure if you have more like security requirements. So in our example today, we'll be running through MLflow. But I do recommend trying weights and biases because it seems to be quite popular, and people have been using it for their university thesis projects, for example. So the next concept that I really want to talk about is SageMaker Jumpstart, because it really ties into our last lecture, which is on generative AI. So SageMaker Jumpstart is a service that allows you to load in pre-trained models. And by pre-trained models, I mean models that have, you would use because you don't need to train your model. You can basically fine-tune a already trained model and deploy it to serve different purposes. So for example, you can basically load in models like YOLO. So YOLO is a very popular high-performance computer vision kind of model where you can do like video detection, and you can basically load it and then easily like fine-tune it for your purposes and then deploy it onto an endpoint. So it looks something like this. Basically, you have your data, you load it in the S3, and then you kind of like load the model from SageMaker Jumpstart into your notebook. And then from there, you can deploy it onto an endpoint, and then it can run like the pre-trained algorithm. And the examples that are out there tend to be for supervised learning. You kind of use like pre-trained models like SGBoost or KNN. So you can easily like load the model in, and you don't really have to set up yourself. For unsupervised learning, there's stuff like k-means clustering, as well as random cut forests that you can load in. And there's also a lot of other different models, for example, for time series prediction and so on. Where SageMaker Jumpstart really excels is in the realm of generative AI, because SageMaker Jumpstart allows us to load in pre-trained diffusion models, for example, that we can then use to generate images and so on. So this is an example of how you would deploy SageMaker Jumpstart in a like production environment. So you would have your image generation model. So for example, Stable Diffusion, or text generation models like BERT and so on. Basically, you can load it up from SageMaker Jumpstart, and then you can deploy it under the hood. It's kind of deployed as an ECR. ECR stands for Elastic Container Registry, and it basically is a image registry for containers, and then it can be loaded onto SageMaker endpoints and then deployed via an API gateway and Lambda function. They kind of serve as a serverless inference kind of endpoint where you can then like generate images or generate text for your web application. So this is how you deploy it in an integrated application. And yeah, you can look up examples online on how people would deploy this. So our hands-on will basically involve kind of showing how MLflow works. So MLflow is an experiment tracking tool, but beyond just that, it also allows you to kind of basically run your whole end-to-end ML pipeline. So that pipeline basically includes training, it includes experiment tracking, and basically kind of having like a centralized repository for all your ML workflows. But before we go into that, we basically first need to understand that MLflow kind of requires you to deploy your own infrastructure. And by your own infrastructure, I mean like either SageMaker, which is basically a wrapper around like different compute engines, or you could deploy it onto like bare metal, for example. So you would need to have your own infrastructure in place if you want to use MLflow. Whereas for weights and biases, a very cool thing is that they have kind of a SaaS offering. So instead of having to manage your own infrastructure, you can actually just use their SaaS offering to kind of like perform your ML workflows. So the first concept that I've went through very quickly just now was Amazon Elastic Container Registry. ECR is basically a tool that allows you to store different images of your containers. And then you can basically push these images to Amazon ECR, and then subsequently your different applications or other users in your team can then securely download and use these images for different purposes. The next kind of service is Amazon Fargate, AWS Fargate, which is basically a serverless container deployment offering. So basically what that means is, for example, you would have a container that you have an image that you upload onto Amazon ECR, and then Fargate can then take this image and then deploy it as containers for different purposes. And it's serverless, which means that the containers are only deployed when demand increases. So that kind of like helps you to easily scale up and down. We basically, in this project, what we want to do is we want to have a tracking server for ML experiments. So what that means is when we have training jobs, so for example, when we train our model for a certain set of data, we want to track this training job somewhere. And we kind of have this model registry in SageMaker, as well as track these different training runs using MLflow. And subsequently, we want to deploy it onto SageMaker endpoints or SageMaker batch predictions, which allows us to perform different inference styles. So previously I mentioned that you have real-time and you have batch. So basically, based on the different purpose of your deployment, you kind of use different like deployment styles. So like either batch or like endpoints, basically. So this basically has us to deploy MLflow onto Fargate. So what we'll do is we will wrap up MLflow into a container. Then after we upload the image onto ECR, Fargate basically takes that image and deploys it as a serverless container kind of platform to be used when our team has machine learning workflows that they want to run. RDS and S3 is there to store different metadata that is associated with our MLflow server. So you as a user, you would be able to like log in via the load balancer, and then subsequently you would be able to track your different machine learning workflow runs. And our intent in this case is to run a few experiments to kind of predict housing prices using the random forest algorithm. You can follow this workshop using the tinyURL link over here. It leads you to a AWS blog, and the blog is the one that I followed to kind of set all of this up. So let's go into the code. So as with last time, we had a CDK kind of setup. So you would be kind of familiar with how CDK setup is like after like the past few tutorials. So now it's not too different. We also have our ML infrastructure set up as a CDK project. So in this case, we are using the different services that I mentioned earlier, and we kind of set up the groundwork for our ML flow container to be deployed onto the cloud. As with last time, some things to take note of is your roles. So you would have IAM, which is the service to kind of assign roles to different parts of your infrastructure. So in this case, we want to give like full S3SS as well as like full access to ECS to our infrastructure. And also we have a VPC. So VPC, I might not have went through this before, but VPC stands for Virtual Private Cloud. And you can think of it as like a cloud, a private cloud within the public cloud. And this allows you to kind of like basically enhance security by keeping everything like connected privately within your architecture. So in this case, we kind of use the VPC to set up a network for our EC2, which is our compute clusters. We set up S3 bucket, as I mentioned, to keep ML artifacts. So you can think of it as like kind of metadata associated with your ML models. We also set up a RDS service. RDS is the relational database service. And then we also type in different metadata that's associated with RDS. So for example, we want to use MySQL as the database engine for RDS and the other configuration needed to connect it to our VPC. Here we set up Fargate. So Fargate is the serverless container platform. And Fargate basically uses ECS, which is Elastic Container Service, to set up the different containers that is required to run our workflows. So over here, we key in the configurations that we want, which is that we want it to kind of obtain the ML flow image from ECS. So this allows us to obtain the ML flow image and then deploy it on Fargate so that when our data scientists need to run their experiments, it basically allows ML flow servers to be stood up and to track their experiments. So a bunch of other configurations associated with Fargate. And the key thing note is that we have a load balancer over here, which is the front for our Fargate server. And we basically have it as output after our CDK infrastructure has been deployed. And then we can then access our MLflow server via this load balancer DNS. So I've already done it over here. I've already run CDK Bootstrap as well as CDK deploy. So if you want to do this as well, you can also run CDK Bootstrap and deploy at home. So if you've run it correctly and nothing goes wrong, you would be able to see the MLflow kind of overview over here, which is something that you can access via the DNS. So I've keyed in the DNS, which is outputted over here. DNS stands for domain name service. For those that don't really know, it basically is a mapping of kind of like a URL. So for example, facebook.com or google.com to an IP address, and then you'll be able to access the IP address, which points you to your server via this URL. So our DNS URL is over here. So if you type this in, you would basically be forwarded to this MLflow server. So all our experiments can be tracked within this MLflow server. Yeah. So the key thing to note is you kind of have your notebooks. So if you go back to the architecture, you will see that our notebooks are kind of like being used to run the different jobs. So SageMaker allows us to stand up different instances to run different notebooks. So you know that machine learning tends to use heavy GPU workloads. So in this case, we are able to stand up instances that use GPUs. So there are different classes of instances. You know that EC2, there's the free tier, which has, for example, T2 micro. But there are also machine learning optimized instances, for example, that use they are like this. So MLT3 medium basically is GPU optimized, allows you to run heavy ML and deep learning workflows on it. So if you were to run spin up a instance using SageMaker, you would basically be able to access it, and it would be the typical interface that you would use Jupyter Lab for. So you could also do it on your own computer, but since your computer might not have the GPU compute to run the workflows, it would be much easier and much faster to spin up an instance on SageMaker notebook and then subsequently run your experiments there. Oops. So I've already run Jupyter Notebook. So there are three different notebooks associated with this example. So the first is to train the scikit-learn model in SageMaker and have it be tracked in MLflow. The second is to kind of demonstrate the hyperparameter optimization capabilities of SageMaker. And the third is to deploy it onto a SageMaker endpoint. So I kind of run like some of the steps previously. So something that you basically do over here is you would key in your MLflow server URL, and then this can get subsequently forwarded to your training code to then be used to lock your MLflow run. Yeah. But basically, yeah, so basically I tried to run it previously, but I kind of got an error. And yeah, I kind of need more time to debug this. But if you go back, you can basically go and try it out and see whether it works for you. Then you can see like MLflow tracking your experiments. So just want to, before I like hop on further, I want to show you how to deploy something onto SageMaker endpoint. So if I go back to over here, my notebooks, oops. Yeah, so this is a deployment notebook. Basically, what you can do is you can build an image with MLflow to serve your model. So after you build the image, which basically contains your trained model, you can just deploy it on the SageMaker using the SageMaker SDK. So you can basically like point it to your model URL over here, and then you would give it different configurations. So here, for example, the configuration is that we want to have our instance be ML M5 X large. So that is the instance associated with how our model, the compute that it uses to perform inference. And then we subsequently create a deployment over here, as well as like with the different settings that we want to have. So here is basically, for example, we want to use Python for our deployment. And then subsequently, we can basically try it out. We can have our data be loaded and then used to predict. And then we obtain the prediction after basically an API call. So all this does is it basically takes the first row of the data frame, which is our data, and then it performs inference and returns the predicted housing price based on our trained model. So you can just follow this. I didn't really have time to kind of test everything out, but if you were to try it at home, I think you would be able to see MLflow kind of work for you, where you would be able to see like the different models, different runs kind of be tracked. So I really kind of recommend also trying weights and biases, because weights and biases is also kind of really good. It has very good visuals for you to observe like your different hyperparameter optimization runs, as well as like your different models that you've trained. So going back here, if you want to extend further, there's also the service, which is SageMaker pipelines. So this allows you to kind of stage a end-to-end MLOps pipeline that allows you to continuously train and update your model, as well as create different stages. So you would have an endpoint for staging, as well as endpoint for production. And this allows you to kind of prevent like buggy models from being deployed onto production. So, as you can see, there is a lot of work associated with having ML workflows be deployed in a scalable, secure, and observable manner onto the cloud. There are different services that you can leverage. We went through different experiment tracking services. We talked about feature stores. We also talked about monitoring dashboards and endpoints. And this helps you to take your models from being just trained in your notebook to something that can be deployed onto applications or for different users to basically service. So next lecture, which is going to happen next Thursday, we'll be going through the basics of large language models. We'll go through a quick summary of what transformer networks are, as well as like go through LangChain, which is a very popular orchestrator for large language models. So if you want to do like prompt engineering of a large language model, you can use LangChain to kind of like automate that, as well as like talk a bit about retrieval augmented generation and kind of share how it looks like. Basically, how organizations would deploy retrieval augmented generation to allow like large language models to have knowledge of their data to perform like chatbots, for example, that are able to respond with knowledge of an organization's data. So if not, that's all I have. I think the pizza is still on its way. So if you are here for a pizza, I suggest you stay a bit more. If not, thank you so much for coming, and yep, have a great evening.